All right. Hello, algebra. Whoa, wait a second. Hello, geometry honors. This is our final lesson in chapter 3, and it's lesson 3.6, prove theorems about perpendicular lines. And I will let you know up front that you're not going to use these theorems in any proofs that are on any assessments, but you're actually going to use the relationships. But you're not going to have to fill out any proofs using these theorems. So we've got a few theorems to look at. The first one I'm going to call the congruent linear pairs theorem. And I just kind of made that name up. But it says if two lines intersect to form a linear pair of congruent angles, so linear pair, but then you know these are congruent, then the lines are perpendicular. Yeah. I think that kind of makes sense if you kind of take some time to think about it, how if you're linear pair, then you're supplementary. If you know that they're the same measure, then they're each going to have to be 90, and if they're 90-degree angles, then they're perpendicular. Theorem 3.9 doesn't really have a good name for it, but it says if two lines are perpendicular, then they intersect to form 4 right angles. So if you know that they're perpendicular, then you know that you at least have one right angle. Well, in truth, you're going to have 4 of them total. And you can get there by like vertical angles congruence theorem or linear pair postulates, stuff like that. You can figure out all those. But I think this makes sense. I think it's good. All right, we're not going to have to use these theorems in any proofs, but let's prove one of these theorems. So theorem 3.8, the congruent linear pairs theorem. Let's do a proof of this. This proof looks kind of intimidating with all the steps involved, but in truth, each step is pretty straightforward. So they already have the given in there for us. So step 2 says angle 1 and angle 3 are supplementary. Well, how do we know that? We know that because they were linear pair. So when that happens, when you know something because of a very specific word, chances are that's a definition. And in this case, it's definition of a linear pair. Step 3, measure of angle 1 plus measure of angle 3 is equal to 180. Well, how do you know that? Well, you know that because they're supplementary. And so here we go again, definition of supplementary. Now, next up, they say measure of angle 1 equals measure of angle 3. Now, that doesn't actually come directly from steps 2 and 3. It comes from step 1, or statement 1, where it says angle 1 is congruent to angle 3. Well, if they're congruent, we know that their measures are equal. And yet again, we got another definition of congruency. Or you could say definition of congruent angles if you want to get more particular about it. Now you might be thinking, well, why would we do that step to change it? One thing that you got to realize is there's no substitution property of congruence. So I feel a substitution property coming on here. So that would be one reason why they would need to convert these. All right, next up we've got measure of angle 1 plus measure of angle 1 equals 180. Well, that's essentially this statement here, but what have they replaced measure of angle 3 with? Measure of angle 1. And so, yeah, there it is, actually. There's substitution. Property of equality. And the next step comes directly from statement 5. Do you agree that measure of angle 1 plus measure of angle 1 is going to equal 2 times the measure of angle 1? Well, you could think of that as simplifying. Or you could be more specific and say that it's combining like terms. And then for the next step, to go from statement 6 to statement 7, you're going to use a property of equality. And yep, that's right, it's the division property of equality. And then we're in the home stretch here. Statement 8 says angle 1 is a right angle. Well, shucks, we knew that because the measure of angle 1 is 90. That's going to be definition of a right angle. And then we wrap things up. If you know it's a right angle, you know that the lines have to be perpendicular. And that's because that's the definition of perpendicular lines. All right. So yeah, there's a proof there of theorem 3.8. Let's flip it over. Theorem 3.10, it says that if two sides of two adjacent angles are perpendicular, so we've got adjacent angles, and we know that this side is perpendicular to this side, well then we must know that the angles are complementary. And I think this kind of makes sense. The setup for it is a little bit, it takes a lot. They got to be adjacent angles. Two sides are perpendicular. So yeah, so basically you've got, let's call it angle 1 and angle 2. We know that angle 1 and angle 2 are complementary. What's up?
Sorry, I didn't know if you were like recording or anything.
I am actually, but you're good. Actually, I'll be done in just a second. Can I'll come by, okay?
That's perfect.
Awesome. In example 2, it says in the figure, angle 1 and angle 2 are congruent. So I'll go ahead and mark that with our arc marks. Whoa, got a little crazy there. What can you conclude about the measure of angle 2? Well, we just learned that if we've got a congruent linear pair, we know that the lines are perpendicular, which means the measure of angle 2 is 90. Nice. All right. These last two I feel are really straightforward. Super straightforward. Theorem 3.11 says perpendicular transversal theorem. It says if you've got, let's read it out. If a transversal is perpendicular to one of two parallel lines, then it is, and the statement is, then it is perpendicular to the other. And I'll tell you why this makes so much sense. Well, if you've got two lines and you want to say they're parallel, you can put an extra set of arrows on there. And then you've got this transversal, and you know that the transversal is perpendicular to one of them. Well, essentially by the corresponding angles postulate, you're going to know that this angle here is a 90-degree angle as well. So that's kind of a justification of it. But yeah, once you know one of them, you're going to know the other. If they are parallel. If they're parallel, if you know one, you know the other. Theorem 3.12 is almost the converse. It says if two lines are perpendicular to the same line, then they are parallel. So it's kind of going the opposite direction. Let's draw them this way just for kicks. So you got two lines. We don't know they're parallel, but we do know that this transversal is perpendicular to both of them. Let's call this one L and this one K. If the transversal is perpendicular to both of them, then what do we know about L and K? They're parallel. All right, so example 3 says determine which lines, if any, must be perpendicular. Explain your reasoning. Well, I'd encourage you to pause the video for a second and see if you can figure out which lines, if any, must be perpendicular, and think about what your justification for that is. So it turns out we know right out of the gate that C is perpendicular to B. In a sense, that was given to us. We were given a right angle there. Boom. Definition of perpendicular right there. But is that it? Well, I would argue, no, that's not it. We know some other relationships here. If this is 76 degrees and this is 76 degrees, those are corresponding angles. And if we have corresponding angles the same, we know that A is parallel to B. Essentially, it's the corresponding angles converse. If you know corresponding angles are congruent, then you know that the lines are parallel. And therefore, if these lines are parallel and one of them's perpendicular, we know that the other intersection is also perpendicular. So we can say that C is perpendicular to A. So our reasoning, we've got a corresponding angle converse to get parallel lines. And then I believe this is the perpendicular transversal theorem. If we know these are parallel and the transversal is perpendicular to one, we know the transversal is perpendicular to the other. So that's how we know that C is perpendicular to A. So I guess we could write perpendicular transversal theorem. As a little justification there. All right, so that's basically it. But there's something else that is in the practice for this section that kind of sneaks up on us a little bit. And it's something we've talked about before, but basically it's talking about the distance between objects. Well, if you're going to find the distance between a point and a line, if you're going to find the distance between them, you're not going to measure this length. You're not going to measure this length. You're going to measure the shortest distance, which is always going to make a right angle with the line. So the shortest distance between a point and a line is always a perpendicular segment there, a perpendicular segment to the line. So there's going to be a couple problems that test that knowledge, that check that knowledge. Additionally, they're going to ask you to use the distance formula to calculate the distance between two objects. And so what you're going to have is you're going to have some coordinates, and then you can use the distance formula. And the distance formula is pretty forgiving. You just got to remember to subtract the x's subtract the y's, square them both, add them together, and then finally take the square root of both. The reason I say it's forgiving is the order doesn't matter. You just got to do x's together, y's together, square it, add them up, and then take the square root. So there's going to be a couple of problems that involve doing that. All right, so page 194 is your practice. Numbers 2 through 10 and 13 through 23. And then there's a little bit of review over circumference and area of a circle. I think that's going to be a little bit of good review for you right there at number 42. So practice this, you'll know it better. Thanks a lot.